Module 2, Machine Learning Fundamentals. 201, Supervised Learning. Definition and overview. Supervised learning is a type of machine learning where an algorithm learns to map input data to output labels based on a set of labeled examples. The goal is to learn a function that can predict the correct output for new, unseen inputs. Types of supervised learning tasks. Classification. In classification tasks, the algorithm learns to assign input data to discrete categories or classes. Examples include spam email detection, image classification, and sentiment analysis. Regression. In regression tasks, the algorithm learns to predict continuous numerical values based on input data. Examples include predicting housing prices, stock prices, or weather forecasts. Training process and model evaluation. Training data. Supervised learning algorithms require a labeled data set for training, where each example consists of input features and a corresponding output label. Model training. During training, the algorithm adjusts its internal parameters to minimize the difference between its predicted outputs and the true labels. This process is typically done through optimization techniques like gradient descent. Model evaluation. The trained model is evaluated on a separate test data set to assess its performance and generalization ability. Common evaluation metrics include accuracy, precision recall, and F1 score for classification tasks, and mean squared error, MSE, or mean absolute error, MEA, for regression tasks. Popular supervised learning algorithms. Linear and logistic regression. Decision trees and random forests. Support vector machines, SVM. Naive Bayes. K-nearest neighbors, CAN. 2.2 Unsupervised learning. Definition and overview. Unsupervised learning is a type of machine learning where an algorithm learns to find patterns and structures in input data without the need for explicit output labels. The goal is to discover hidden relationships or groupings within the data. Types of unsupervised learning tasks. Clustering. Clustering algorithms group similar data points together based on their inherent characteristics. Examples include customer segmentation, document clustering, and image compression. Dimensionality reduction. Dimensionality reduction techniques aim to reduce the number of features in high-dimensional data while preserving its essential structure. This can help in data visualization, noise reduction, and computational efficiency. Examples include principal component analysis, PCA, and TSNE. Anomaly detection. Anomaly detection algorithms identify rare or unusual instances that deviate significantly from the norm. This is useful in fraud detection, system health monitoring, and network intrusion detection. Applications and real-world examples. Customer segmentation for targeted marketing campaigns. Topic modeling in text data. Image compression and feature extraction. Anomaly detection in financial transactions or manufacturing processes. Popular unsupervised learning algorithms. K means clustering. Hierarchical clustering. Gaussian mixture models. Principal component analysis, PCA. TSNE, T-distributed stochastic neighbor embedding. 2.3 Reinforcement learning. Definition and overview. Reinforcement learning, RL, is a type of machine learning where an agent learns to make decisions by interacting with an environment. The agent receives rewards or punishments based on its actions and aims to learn a policy that maximizes its cumulative reward over time. Key concepts in reinforcement learning. Agent. The learning entity that makes decisions and interacts with the environment. Environment, the world in which the agent operates and receives feedback. State, the current situation or a condition of the environment. Action, the choice made by the agent at each state. Reward, the feedback signal that the agent receives from the environment based on its actions. Policy, the strategy or decision-making rule that the agent follows to choose actions. Reinforcement learning algorithms. Q-learning, a value-based algorithm that learns the optimal action value function, Q function, to guide the agent's decisions. SARSA, state action reward state action, another value-based algorithm that considers the actual next action taken by the agent during learning. Policy gradient methods, algorithms that directly optimize the agent's policy by estimating the gradient of the expected cumulative reward with respect to the policy parameters. Applications and real-world examples. Game playing, e.g. AlphaGo AlphaStar. Robotics and control systems, autonomous vehicles. Resource management and scheduling. 2.4 Neural networks and deep learning. Overview of artificial neural networks. Artificial neural networks, ANNs, are computational models inspired by the structure and function of biological neural networks. They consist of interconnected nodes, neurons, organized in layers, which process and transmit information through weighted connections. Types of neural network architectures. Feed-forward neural networks, the simplest type of neural network where information flows in one direction from input to output layers. Convolutional neural networks, CNNs, specialized neural networks designed for processing grid-like data, such as images or time series. They use convolutional layers to learn local patterns and features. Recurrent neural networks, RNNs, neural networks designed for processing sequential data such as text or speech. They have feedback connections that allow information to persist across time steps. Autoencoders, neural networks used for unsupervised learning tasks such as dimensionality reduction or feature learning. They learn to compress and reconstruct input data through an encoder-decoder architecture. Deep learning and its impact. Definition of deep learning. Deep learning refers to neural networks with many layers, deep architectures, that can learn hierarchical representations of data. Advancements in deep learning, the availability of large datasets, increased computational power, GPUs, and algorithmic improvements have led to significant breakthroughs in deep learning performance across various domains. Applications of deep learning. Deep learning has achieved state-of-the-art results in areas such as image and speech recognition, natural language processing, and game playing. Training deep neural networks. Backpropagation algorithm, the key algorithm for training neural networks, which propagates the error gradient backward through the network to update the weights. Optimization techniques, methods like stochastic gradient descent, SGD, ATOM, and RMSprop are used to efficiently optimize the network's parameters during training. Regularization methods, techniques such as L1-L2 regularization, dropout, and early stopping help prevent overfitting and improve generalization. Challenges and future directions. Interpretability and explainability. Deep neural networks are often considered black boxes, making it difficult to understand their decision-making process. Research on interpretable and explainable AI aims to address this challenge. Unsupervised and semi-supervised learning. Developing methods to learn from unlabeled or partially labeled data is an active area of research as it can reduce the reliance on large labeled datasets. Transfer learning and domain adaptation. Techniques that allow neural networks to transfer knowledge learned from one task or domain to another, improving efficiency and performance. Continual and lifelong learning, enabling neural networks to learn continuously and adapt to new tasks without forgetting previous knowledge, similar to human learning. This module provides a comprehensive overview of the fundamental concepts and techniques in machine learning, covering supervised learning, unsupervised learning, reinforcement learning, and neural networks. By understanding these core concepts, learners will be well equipped to explore more advanced topics and applications in the field of artificial intelligence and machine learning.